In this video, we're going to continue with chapter 4, and it's going to focus mostly on cyclic alkanes or cycloalkanes. Remember, cycloalkanes are still hydrocarbons, right? It's still just carbon and hydrogen, but they are actually unsaturated, right? They are not saturated. They don't follow the CnH2n plus 2 rule, right? When we take the two ends to connect them to form the ring, we do have to remove a hydrogen from each carbon. So these are hydrocarbons, but again, they are not saturated, they are unsaturated. So singly bonded carbons in a ring. We did look at in a previous video that because they're in a ring, they're locked in place, right? Like an acyclic alkane. Remember something like this, if I wanted to put a bromine here, and we could put a bromine on this carbon also. And because I just have a regular sigma bond and it's not in a ring, we can rotate that bond. So we can go from that structure to essentially moving that carbon down. When I do that, this bromine is going to flip back. That hydrogen is going to be out in front. This carbon I didn't change, so I can keep my orientation. And we said that the relationship between these were different conformations. Remember, conformations are essentially different orientations of the same molecule that we get by rotating a bond. Right? If I was to rotate that bond between the two carbons, between carbon 2 and carbon 3, I can go from the one molecule on the left to the one on the right without removing, right? I don't have to break a bond. I just have to rotate a bond. So these we got by rotating a sigma bond. And it's always just going to be a sigma bond that we rotate. We can't actually rotate a pi bond. I talked about this briefly in our previous videos also. And so remember, if I have a single bond, I'm just overlapping in one spot. If I have a sigma bond, right, I have these p orbitals, and remember they're overlapping sideways. They're overlapping on top of the nucleus and then below the nucleus. So because they're in both places, it doesn't have free rotation. Single bonds, sigma bonds though, however, I can rotate like that. So that gave us those conformations. Because our cyclic structure though is bonded to other carbons, it doesn't actually have free rotation. So we actually talked about stereoisomers. So if I was to put two bromines on here, I can't rotate that bond between them and end up with the bromine on the other carbon going back, right? I can't go from here to here by rotating a bond. That's not possible. That makes these guys stereoisomers. The only way to go from the one on the left to the one on the right is to actually remove a bond and then attach it differently. So stereoisomers, these differ only in their three-dimensional orientation in space. If I always be careful, and we can do a summary this week also of kind of the difference between constitutional isomers and stereoisomers. We have resonance structures and conformations now, so it is getting kind of complicated. So just be careful. If I was to compare this original one to this one, these two are not stereoisomers. These are actually constitutional or structural isomers. They actually are different structures, right? Stereoisomers, if we go back up, differ only in their three-dimensional orientation. If I was to name both of those molecules, I'm going to have 1,2-dibromocyclohexane. The first one is trans, the second one is cis, but they're both 1,2-dibromocyclohexane. If I look at these two that I just drew, the first one is 1,2-dibromocyclohexane. The second one is 1,3-dibromocyclohexane, right? The carbon or the bromine is actually on a different carbon in the two structures. So these actually are constitutional isomers, right? They have different connections. Stereoisomers have the same atoms connected to the same atoms. They just differ in their three-dimensional orientation. If I go back up to these guys, they're not actually different because I can get one from the other by rotating a bond, and that makes them conformations. So conformations, stereoisomers, constitutional isomers. Another thing that we want to notice about cycloalkanes is that they have what's called, or some have, what's called angle strain, also called a ring strain. Angle strain and ring strain are the same thing. I usually use the term angle strain. I know in lab they're using the term ring strain, so I'm sorry if that's confusing. But what this is it's taking, if you have a bond angle that's either larger, so it's expanded, or it's smaller, it's compressed beyond what it wants to be. So remember, if something is sp3 hybridized, it's tetrahedral and it wants 109.5 degree bond angles. If it has an angle that's larger than that or smaller than that, it's going to have angle strain or ring strain. So this is due to bond angles either compressed, so smaller than it wants, or expanded, larger than it wants, beyond their ideal. So ideal, what it wants. So if you have something that's sp2 hybridized, its trigonal planar, its ideal bond angle is 120 degrees. So if it's smaller than that or bigger than that, it's going to have angle strain. So if I was to look at cyclopropane, right? Remember, prop is 3 carbons. Propane means they all have single bonds between them, and then cyclo, it's in the form of a ring. So I have 3 carbons in the form of a ring. It essentially looks like a triangle to us, right? Cyclopropane. And if I was to put hydrogens on here, I do have 2 hydrogens on every single one of those carbons, right? It is an alkane. I don't have any charges on there. So those carbons are all sp3 hybridized, right? They're all tetrahedral, or they want to be tetrahedral, which means ideally they want 109.5 degree bond angles, right? This is what they want. This is their ideal. However, if you were to make essentially an equilateral triangle, what are those bond angles, right? What is my angle between here and here? Yeah, good. 60 degrees if you guys came up with that. If you didn't, I'm telling you. 60 degrees, right? If you have an equilateral triangle, the inner part of the angle is going to be 60. So this thing has a ton of angle strain, right? It wants 109.5 degree bond angles, but has 60 degree bond angles. So lots of angle strain. I don't know that lots is actually a word, but we're going to use it. I suppose we should say a lot of angle strain. I want you guys to use college level sentences. I suppose I should too. A lot of angle strain. We're going to give him a big sad face because cyclopropane is not a happy molecule. It's really high in energy. It's pretty reactive because of that angle strain. It's just not a stable molecule. So lots of angle strain. If I was to actually draw this, I'm going to try to draw it coming in and out of the plane. So right now I have the carbons in the plane of my iPad, and then if I was to indicate my stereochemistry, I have one hydrogen coming out and one going back on each of those carbons. I'm going to switch the orientation, so I'm going to have the ring coming in and out of the plane. So what I'm going to do is I'm going to wedge these carbons. So the ring is coming out at you. And then when I put my hydrogens on, they're going to be essentially going up and down. They're angled a little bit, but so what else does this molecule have going on besides angle strain, right? It has 60-degree bond angles. It wants 109.5, so that makes it pretty unhappy. What else? Do you guys recognize it? It's something that we would have talked about in our last video. Yeah, if you're seeing it, it actually has torsional strain because those bonds are eclipsing each other. Right, this bond is lined up directly with that bond, and this bond here is lined up directly with that one, and this one directly with that one. Those bonds are eclipsing each other. And then the same on the bottom, I have eclipsing bonds, and then around the back. So I actually have 6 areas of eclipsing bonds. And remember, anytime we have bonds that eclipse, we also have torsional strain. So not only does cyclopropane have angle strain because we're forcing it into an equilateral triangle, and it doesn't want that, right? I'm going to show models later, and with the model kit I have, it's hard to even make that because the beads that I have that represent the atoms, the holes that are in them are drilled to have 109.5 degree bond angles, and I'm trying to take hard plastic and make it 60. So you can actually, if you try to make it with one of these models, you can actually like feel the strain trying to make it. And then not in addition to that, right, I have all of this torsional strain. I'm just going to get rid of those arrows because it's probably easier to see it if I don't have them there. So carefully try not to erase other things, which I was unsuccessful in. All right, so another sad face. Cyclopropane is just not a happy molecule. We'll give him a little tear also. Poor guy. Okay. Cyclobutane, and there's not much we can do about this. As we get more carbons, we can actually try to relieve some of the strain, but we're not doing much with cyclopropane. It's just unhappy, right? It's a pretty unstable molecule. Cyclobutane, how many carbons does cyclobutane have? Yeah, good, 4. So bute was 4, it's an alkane. It's in the form of a circle, so this one would look like to draw this one coming in and out of the iPad or your video also. So this carbon that I'm currently wedging is coming out at us. And then the one that's directly across from it is going back. And then when I put my hydrogens on here, I'm actually going to end up with 8 areas of eclipsing bonds. So 4 on top, and then I also have the ones on the bottom. And these ones are angled. They're actually not 180 degrees, the 2 hydrogens from each other, the way that I'm drawing. And we'll look at some models after, but they're still eclipsing down below and on top. So I have 8 areas of eclipsing bonds, which means I do have torsional strain. Quite a bit of it, actually. And then what are my bond angles for cyclobutane? Yeah, good. 90 degrees, right, if I have a square. So it has 90-degree bond angles. It still wants 109.5, right? Those carbons are sp3 hybridized. They're tetrahedral. They want 109.5 degrees. So it also has angle strain or ring strain. So cyclobutane, for some reason I'm having a hard time with that name, can actually do something to try to relieve this strain. So what cyclobutane is going to do is it's going to adopt a non-planar conformation. So instead of keeping all 4 of those carbons in the plane, we're actually going to take one of them and we're going to pop it up out of that plane. So adopts a non-planar conformation. Notice I'm using the word conformation because all I'm doing, I'm not detaching a bond and reattaching it. I'm actually just going to bend one of them up a little bit. I'm going to rotate 2 of the carbon bonds partially to pop one of those out or up. So if I take, I'm just going to leave the hydrogens off here. So if I take this, and I'm going to take this one in the middle, in the front here, that's coming out at us, that carbon, and we're actually just going to move it up a little bit. And we will look, I promise, we will look at some models here. So it's kind of weird to draw. So we're showing that this carbon here that I'm now wedging is actually coming up out of the plane a little bit. What that does is it actually alleviates some of that torsional strain because the hydrogens now on that carbon that's up are not eclipsing the other carbons. So we would say that this is now up. Sometimes we say it's puckered. I don't usually use that word because I think it sounds funny, but we're moving that up and it alleviates some of the torsional strain. It still has angle strain, and honestly it has more angle strain now because we're tightening up some of those bond angles when we do that. So we're adding angle strain to it, but we're alleviating or relieving more torsional strain than we're adding angle strain. So overall it's going to be more stable than when it was planar. So this does increase angle strain some, or ring strain. I should say some, not zoom. But again, it's relieving more torsional strain than it is adding angle strain, so overall it's okay. This structure actually has a name. We would say it's a boomerang. So cyclobutane adopts a boomerang structure because it looks kind of like a boomerang. So let's look at the models for cyclopropane and cyclobutane. So I have, right now it's not cyclic, but I have propane. I have 3 carbons. And I kind of want to show you how hard it is to make so you can see the strain. But when I go to attach these, you're going to have to look kind of closely. My hands are probably all in the way. I have to really I have lotion on, so it's even harder to do. I really have to bend it to get it. And can you see the space? I don't know if it's focused, but there's like space between the carbon atom and that bond there. And you can kind of see how like those bonds are bending. It just doesn't like it. So again, we're taking something that wants 109.5 degree bond angles and we're giving it 60 degree bond angles. Like it's hard to physically make it. I have to really put some some effort into making that sucker. And then if I was to go and put all my hydrogens on here, I'm gonna put them on kind of loosely, so I'm probably gonna lose some in the process. You can see all of those eclipsing bonds. So you know how I said they're not 80 degrees. I was drawing them like 80 degrees in the picture and they're angled, but they're still eclipsing, right? You can see that those, if I line them up, they're directly lined up with each other. So all of these sigma bonds on the top and the bottom, right here and here, and here and here, and around the other side, and then on the top, all of those sigma bonds are lined up directly with the other sigma bonds. So lots of torsional strain in addition to that angle strain. I'm going to stick another carbon in here and make this our cyclobutane structure. I don't have hydrogens on this one because I just stuck the carbon in, but there would be 2 hydrogens on there. And let's actually grab some. You would see that I have even more eclipsing bonds, right? There's 4 areas on top and then 4 areas on the bottom. So again, in my structure that I drew, right, I drew those hydrogens kind of straight up and down, and they're not, they are angled, but they are all eclipsing each other. If you can see how they're all lined up, if I get the angle right. We can't really see the ones in the back very well because they're eclipsing. I have another cyclobutane here. I think this one's going to be easier to see without the hydrogens on it to see the boomerang. So currently it's flat, right? There's nothing, I have a hard time. The camera's opposite, so I'm not quite used to it. It has everything flat, right? It's planar. If I was to put it on a sheet of paper, right? Nothing sticking up, nothing sticking down, it's completely flat. So what we're going to do is we're going to adopt that non-planar geometry. So I'm going to take one of them and I'm going to actually bend it up over the plane. So now if I try to put it on my paper, right, that one carbon is sticking up now. It's not actually flat. So my non-planar geometry. And if I do that with the one that I have the hydrogens on, you can see that I'm not eclipsing anymore, right? This hydrogen or this sigma bond and this sigma bond here, they're not completely lined up anymore. So I relieved some of that torsional strain by adopting that non-planar geometry, by getting in that boomerang shape, right? These 2 are still eclipsing, but this one and this one are not. This one and this one are not, right? It's only every other ones that are now eclipsing. So it's actually more stable this way, even though we added a little bit of angle strain when we adopted that non-planar geometry. Cyclopropentane. Same sort of idea, right? I have 5 carbons, but they're cyclic. And I'm going to draw this one coming in and out of our iPad or screen. So that carbon that I'm wedging is coming out at us. And then if I was to add my hydrogens, as you would imagine, I have even more torsional strain than I did with cyclobutane or cyclopropane, right? I have 5 areas on the top, and then on the bottom, I have 5 areas also. So lots of eclipsing bonds. Right? I keep using the word lots. Lots of torsional strain. An English major, I am not. Sorry, guys. As far as angle strain, it's actually not bad. It doesn't really have much angle strain. It actually has 108-degree bond angles. Still sp3 hybridized, still wants to be tetrahedral, so wants 109.5. So angle strain, not bad, right? But it has a lot of torsional strain. So this one also is going to adopt that non-planar geometry. The reason we couldn't do that with cyclopropane is just the angle strain was so bad. Like, we do make angle strain worse with cyclopentane and cyclobutane when we do this, but we're relieving enough torsional strain to do that. With cyclopropane, its angle strain is just so messed up to begin with that you just can't do that. We just can't make the angle strain worse and expect them to still be bonded to each other. And it doesn't have as much torsional strain as cyclobutane and cyclopentane. So there's really nothing that cyclopropane can do. Cyclopentane, on the other, is going to adopt our non-planar geometry. Again, it's a conformation. Right? In the video that I just showed you with the model, right, with our cyclobutane. I didn't have to detach an atom to do that. I just rotated the bond. I didn't rotate it all the way around, but I did rotate the bond. I bent it up. So it adopts a non-planar geometry. That's a G, which is a conformation. So we're going to do the same thing. I'm going to take that one that's coming out at us, and you can do any. It's just easier to draw it this way, I think. So if I look at this guy again, I'm going to leave the hydrogens off this time so it's easier to see. We're going to take this carbon that's right coming out front, and I'm going to bend that up, just like we did with cyclobutane. So it's now going up. And same sort of idea. I am increasing angle strain a little bit. It didn't really have much to begin with, so we're okay with that. And I'm alleviating quite a bit of torsional strain when we do this. This is called an envelope structure. It's supposed to look like an envelope, like upside down envelope. I guess if you were to like connect that part. Don't though, there's no bonds there. But an envelope structure. Cyclohexane, I think you guys are probably getting the deal. We're going to spend most of our time, however, on cyclohexanes. Cyclohexane is the most common cycloalkane. So essentially the rest of this chapter is going to be on cyclohexanes. And if we were to draw it in its normal planar geometry, again, the orientation I'm choosing is I'm having it coming in and out. So these guys are coming out at you. Right? If I was to go and put all those hydrogens on there, trying to draw it a little more accurate this time, and actually have these bonds bent a little bit. Oops. These back ones are hard to fit on. There's a hydrogen there. It's not actually bumping into that hydrogen because one's below and one's up. Sorry for the bad drawing, but lots, a lot of torsional strain. Right, this time I have 12 areas of eclipsing bonds. And then this one actually does also have angle strain. It actually has 120 degree bond angles. Remember, we have angle strain or ring strain if it's larger as well as smaller than what it wants to be. So it wants 109.5 degree bond angles. It has 120. So it does have angle or ring strain. Or those are bond angles, jumping ahead. Again, it's sp3 hybridized. It wants to be tetrahedral. So angle strain. So just like with cyclobutane, cyclopropentane, this is going to adopt a non-planar geometry. And we're going to actually make two moves on this one. So redrawing this. And I'm not going to wedge it, but it's still coming in and out at us. What we're going to do is I'm going to take one of these carbons and I'm going to bend it up. I'm going to take the carbon across from it and I'm going to bend it down. I guess I will wedge this because I do want you to see it. So this is coming in and out. So what we end up with is called a chair conformation. So they take a little bit of practice to draw, and I've been drawing these for a long time, and honestly I'm not super great at them myself. I can draw this one pretty well, but this thing is going to flip where the carbon that's up goes down and the carbon that down is up, and I find that I don't draw that one nearly as well. I think you'll find that you're probably better at one also. It's standard to not wedge these. If something's in a chair conformation, it's understood that those are coming out at us. So I'm still keeping it in and out as my plane. you don't, like I said, you don't have to wedge those. It's just kind of understood. So like if I was to, let me try to make that better. Kind of like draw an axis down the middle, and then it comes out below, right? It's right down. It's coming in and out at us. So this is called a chair conformation. Again, note that I'm using the word conformation. These are not stereoisomers of each other, right? To go from that planar structure to this non-planar structure, what I'm doing is I'm just tilting, right? I'm bending one carbon up and the other down. I'm not detaching anything and moving it. So it's a conformation. Okay, so our cyclohexane, and the way that I was drawing it is just flat, right? I have it coming in and out at you. I do have hydrogens coming up and down. I'm just leaving them off for clarity, but all of the carbons are just in that plane, right? If I was to put it on a sheet of paper, right? None of the carbons are sticking up, none of the carbons are sticking down. So to put it into our chair conformation, I'm gonna take one and I'm gonna bend it up. I'm going to take another carbon and bend it down. And honestly, it doesn't matter which one goes up and down. You just want two that are opposite of each other. So if I wanted to do these two, that's fine. I just need to take carbons that are completely opposite. One goes up, one goes down. So I'm going to bend this one up, and I'm going to bend this one down. And then we end up with that chair conformation. So this is representing the carbon that's up. These four are still in the plane. They're still flat. And then that carbon is below. If I was, maybe my phone will fit. I should have grabbed something ahead of time. So if I was to look at this, right? Those four carbons around the middle, let me get it all perfect for you those four carbons in the middle are flat on my phone, right? They're still in the plane, one carbon up, one carbon down. So that's my chair conformation. So once I put my groups on those carbons, we actually have two different types of positions. So I'm gonna redraw, and actually let's make it kind of big because I'm gonna mark it all up and I want you guys to be able to see it. So we're gonna draw a chair. I'm gonna try to draw a chair. Like I said, they're a little awkward to draw. I've been drawing these for years, and this is where my lack of artistic ability kind of fails me a little bit. So again, I drew the original one that I drew, I had wedged sections of it. It is standard to not wedge it, but it is in that position. So those four carbons in the middle, these two, are in the plane that's coming in and out at us. So these two are going back, these two are coming forward. This is down, this is up. We always want to try to get in the habit of looking at it from that perspective. So I'm going to use two different colors, and I'm just going to put bonds because it doesn't matter if I have hydrogens on them or if I have methyl groups on them. If I go and add carbon-based groups, I'm adding steric strain, right? We could do that to any of these groups, kind of as a side note, right? If I was to take my cyclopropane molecule and I was to go and put some methyl groups on here, now not only does it have torsional strain, right, between these eclipsing bonds, and then the other eclipsing bonds, I'm just drawing two, but there are bonds to those other carbons, they just happen to be to hydrogen. So not only do I have lots of torsional strain, I still have those 6 areas, and angle strain, but I also just added a whole lot of steric strain between those two groups. So the strain that I've been showing you in this video is kind of the base strain, right? We can make it worse. If I wanted to go and stick a big butyl group on there, well, now I just made that thing so ugly, it probably wouldn't exist. So back to this, guys. 2 different positions. So I'm gonna use 2 colors. And we have what are called axial and equatorial positions. My purple ones are going to be my axial. So the axial ones are going essentially straight up and straight down. If we look at this, the axis I gave it, right through the center, they're along that axis. And they actually alternate every other carbon. So the carbon that's going up is going to have the axial position going up. Always. The axial position on the carbon that's up will always, always, always be up. If you were to do the axial position on the carbon that's up down, you just drew it incorrectly. So on the carbon that's up, axial is up, and then they alternate. So that one was up. This one's going to be down. This one's going to be up. This one's going to be down. This one's going to be up. This one's going to be down. So I just always remember axial's up on the carbon that's up, and they alternate all the way around. The axial position on the carbon that's down is also down. So that's, kind of a check. If it's not down on the carbon that's down, you goofed it up. I'm going to use green. Green are going to be equatorial carbons, and I will write these terms down, I promise. And the equatorial carbons are going to be pointing out around the side, kind of like pointing out towards, like the equator goes around the middle. They're kind of pointing out around the middle. And they are angled slightly up and down, but they're not straight up and straight down like the axial positions are. And they're going to alternate from the axial. So that carbon that's up has the axial carbon up. So its equatorial carbon is going to be slanted down. And notice it's not straight down because it's not axial, it's equatorial. So it's kind of slanted down. This one then is going to be slanted up, slanted down, slanted up, slanted down, slanted up. So they are going to alternate. So my green, these are my equatorial positions. And my purple, these were my axial positions. So I do want us to look at those. We'll take a look at the video or at the model. Okay guys, so I just have it planar right now. We're gonna make it, I have all the carbons on here, we're gonna make it into our chair, and then we'll look at the axial and equatorial positions. So I'm gonna have this carbon going up, and then I'm going to have this carbon going down. So I don't have purple atoms, so we have green atoms. I'm just trying to get it right. And white atoms. So if I look at this carbon that's going up, we'll try to hold it here. I have white is going to represent my axial positions. So if I look, it's straight up, and then this one is straight down, and then straight up, straight down, straight up, and then straight down, or back to where we started. The green ones are representing my equatorial positions, and if we look, it's kind of hard to see when everything's on here, but this is the carbon that's up. It has the axial that's up, so then its equatorial is down a little bit. So the green ones here are my equatorial positions. So down, and then if I look, this one's slanted up a little bit, this one's slanted down, I rotate it, slanted up, slanted down, and slanted up. So they alternate every other way. If you just focus on the white ones right now, right, the white ones are pretty much straight up and straight down, and every other carbon they're alternating. And then if you look at the green ones are slanted, they all kind of go out to the middle, but then they're sloped a little bit, right? This one's sloped up a little bit, this one's sloped down a little bit. So my axial and equatorial positions.